One of the most common reactions for aldehydes and ketones is nucleophilic addition reactions. Now, there are two pathways for nucleophilic addition reaction depending on the nucleophile. The most common pathway is where a nucleophile attacks the carbonyl. That leads to breaking the double bond of the carbonyl, placing a negative charge on the oxygen, and this gives us a tetrahedral intermediate. The tetrahedral intermediate is then protonated by acid, usually in the second step of the reaction, and that will give us a product that typically has an alcohol and a nucleophile attached to the same carbon, the carbon that used to be part of the aldehyde or the ketone. With other nucleophiles, mainly amines, the nucleophile will add, similar to the first step, leading to breaking the carbonyl, giving us a tetrahedral intermediate. But the second step of this mechanism is where the reaction differs. Instead of the tetrahedral intermediate being protonated, instead we lose a water molecule. So usually the proton transfer occurs where this oxygen is first protonated by the amine that just added in the tetrahedral intermediate, and then the lone pairs on the nitrogen will push out the water molecule to give us a double bond between carbon and the nucleophile. In most cases, this will be a nitrogen here that just added from an amine. In general, aldehydes are more reactive towards nucleophiles than ketones. One explanation for this is the fact that aldehydes are less sterically hindered. By definition, aldehydes will have a hydrogen as well as an alkyl group. So for example, here we have acetaldehyde, which has a methyl group and a hydrogen on the carbon of the carbonyl. Compare that to a typical ketone, for example, acetone, which has a couple of methyl groups. The ketone is going to be clearly more sterically hindered. Note that nucleophiles generally add at a 75-degree angle to the plane created by the carbonyl and the three groups around it. So you can see here that angle of attack comes at this 75-degree angle, and that's true for both ketones and aldehydes. An explanation for aldehydes being more reactive towards nucleophiles is the fact that there is only one alkyl group attached to the carbon. Remember, alkyl groups are electron donating. This alkyl group would donate electron density towards this carbon and tamper down some of the reactivity of this carbon, which is electrophilic. Clearly, you can see that by the partial positive charge that it has. Compare that to a ketone, which has two alkyl groups that are electron donating, and so there will be less of a partial positive charge on this carbon of a ketone than the carbon of an aldehyde in the carbonyl. There are other factors that will alter the reactivity of certain carbonyls. For example, if we add electron withdrawing groups, generally that will make a ketone or an aldehyde more reactive than a parent aldehyde or ketone. And if we add an electron donating group, like an alkyl group, generally the carbonyl becomes less reactive. Here's an example of three different ketones. The first one has a nitro group in the benzene ring. The nitro group is an electron withdrawing group. We can clearly see that by the fact that you have a nitrogen and two oxygens, which are all electronegative atoms. And so that nitro group withdraws electron density from the carbonyl carbon of this ketone, and it makes it more electrophilic. The way you can think about it is it has more of a partial positive charge on that carbon. Compared to acetophenone, which is shown here in the middle, with no electron withdrawing group. If we add an alkyl group like a methyl group somewhere on the molecule, usually that will lead to donating electron density towards the carbonyl, and so there's less of a partial positive charge on that carbon of the carbonyl of this ketone, and so it should be less reactive than acetophenone, which is the molecule in the middle of these three examples. Generally, when we add a Bronsted or a Lewis acid to a ketone or an aldehyde, it will make that carbonyl more electrophilic than without it. We can clearly see some examples here with acetone. If we add a Bronsted acid like sulfuric acid, the oxygen of the ketone will be protonated. It puts a positive charge on the oxygen, and so that tends to act or behave like an electron withdrawing group. And so the carbon of this carbonyl becomes more electrophilic. It has more of a partial positive charge than acetone itself. The same thing happens with a Lewis acid, for example, trichloro or aluminum trichloride. When the carbonyl donates electrons to aluminum, which is a Lewis acid, it'll create an intermediate very similar to when we protonate the carbonyl. And so once again, the carbon of the carbonyl becomes more electrophilic, more reactive towards nucleophiles. Sterics around the carbonyl will also play a role in the reactivity. For example, here we have acetone and a substituted ketone with several methyl groups around the carbonyl. So we have mentioned that alkyl groups are electron donating. They generally lower the reactivity of the carbonyl. Well, when you place them near the carbonyl, it makes it even less reactive, not only because of donating electron density, but also because of sterics. So these methyl groups will hinder an incoming nucleophile that wants to react with this carbonyl carbon. Let's look at some examples of nucleophilic addition reactions. The first one we'll look at is hydration. This is where water adds as a nucleophile to a carbonyl. Generally, this reaction is slow when it's simply we simply put a carbonyl in water. We can speed up the reaction by adding an acid or a base. So we'll first look at acid catalyzed hydration of ketones and aldehydes. When an aldehyde or a ketone reacts with water, we create a diol, a 1,1 diol, meaning the two alcohols will be on the same carbon. An example is shown here with acetone reacting with water, producing a hydrate or a 1,1 diol, another name for it. This reaction is reversible, meaning if we start with the hydrate, we can go back to acetone and water. The equilibrium or where this equilibrium lies depends on the carbonyl we're using, but in most cases, usually the carbonyl will be favored over the hydrate. One exception to that is formaldehyde. Formaldehyde, the equilibrium is favored towards the hydrate. As I mentioned previously, reaction of water with a ketone generally is slow under neutral conditions, but we can speed up the reaction if we add an acid catalyst like sulfuric acid. The equilibrium direction will not change, so acetone will still be favored over the hydrate, but we can achieve equilibrium faster by throwing an acid catalyst. Here's a look at the mechanism for this reaction. The oxygen of the carbonyl will be protonated by sulfuric acid. Sometimes you might see this mechanism as instead of using sulfuric acid, we might see the hydronium ion here, which is the product from sulfuric acid reacting with water. This produces this protonated acetone molecule that will react then with water. Water is not the best nucleophile, and so by throwing in an acid, we can protonate this carbonyl, make it more reactive than acetone. And so this nucleophile, which is generally considered a poor nucleophile, will add to the carbonyl carbon, break the double bond to create this tetrahedral intermediate, which will then lose a proton. So we can use the conjugate base of sulfuric acid. We could use a water molecule here to remove this hydrogen, remove the positive charge on this oxygen, and that gives us the hydrate. Ketones and aldehydes can also occur through base catalyzed reactions. For example, we can use sodium hydroxide to speed up this reaction. The base catalyzed hydration of ketones occurs this way. The hydroxide ion is a very good nucleophile, much better than water is. And so the hydroxide ion would directly attach to the carbonyl carbon and break the double bond. Compare this to the acid catalyzed hydration, where we're using water as a nucleophile. That reaction generally starts by protonating the carbonyl first, and then water can now react with a better electrophile, the protonated carbonyl. Continuing with this mechanism, once the nucleophile attacks the carbonyl, we produce this tetrahedral intermediate. The oxygen will now be protonated by water to create the hydrate. This question will take a look at the hydrate of trichloroacetoaldehyde. So take a moment to predict the product that will result from a hydration of this ketone. If water adds to trichloroacetoaldehyde, the result would be as follows. So water would add to the carbonyl, break the double bond, create this tetrahedral intermediate, which will then lead to a proton transfer. This oxygen will be protonated. This one will lose a proton to form the hydrates. And so this is the product that we get from a hydration, whether it's acid catalyzed or base catalyzed of trichloroacetoaldehyde. Another nucleophile we can use with aldehydes and ketones are alcohols. Addition of two equivalents of an alcohol to an aldehyde will produce an acetal. Similarly, a ketone will react with two equivalents of an alcohol to produce a ketal. Note that these two terms, acetals and ketals, are sometimes used interchangeably, and sometimes you might catch me doing the same. But technically, ketals are the products from an addition of an alcohol to a ketone, and acetals are the products that you get from an alcohol adding to an aldehyde. The reaction between alcohols and ketones and aldehydes is generally slow under neutral conditions. We can speed up that reaction by using an acid catalyst. Here's an example with cyclohexanone. If we use two equivalents of methanol and HCl as a catalyst, we can get the corresponding acetal or ketal, whichever term you want to use. Think of the product here as forming from the methoxy groups, adding to the carbonyl twice to produce this acetal. The byproduct from this reaction will be water. Now notice this reaction is reversible, and we can start with an acetal or ketal and reverse it back to the corresponding ketone by using water and an HCl catalyst or some other acid catalyst to push that reaction towards the ketone. Since this is a reversible reaction, we can take advantage of Le Chatelier's principle. So using an excess of alcohol, for example, will push the reaction towards products. Removing the water will also push the reaction towards the products. We can reverse the reaction by adding water or removing the alcohol. One simple way of doing this in a lab would be distilling the alcohol. If we were trying to get the acetal, we might distill the water or use some sort of drying agent within the reaction that will soak up the water and push the reaction towards the acetal. Look at the mechanism for an acid catalyzed alcohol addition to a ketone or aldehyde. So it starts by the ketone being protonated by the acid, in this case, hydrochloric acid. That gives you a protonated ketone. Then that allows an alcohol, which is not the best nucleophile, to add to the carbonyl carbon. This protonated ketone is now more electrophilic than the original ketone. And so upon addition of this poor nucleophile, we break the double bond of the carbonyl. We have now a tetrahedral intermediate, which loses this proton. This is the alcohol that just added. It's going to lose a proton. We could use water. We could use the chlorine from HCl that is produced from the first step. Anyways, whatever base we use is going to remove the proton and then also remove the positive charge on this oxygen. And that will lead us to this intermediate called the hemiacetal. Think of a hemiacetal as it's essentially half of an acetal. It is the halfway point between going from a ketone to an acetal. Sometimes we use the term hemiketal when we're referring to a ketone intermediate. But again, these two terms, hemiacetal and hemiketal, are used interchangeably, and I'm going to probably do that as well several times. This is the second part of the mechanism. So starting with the hemiacetal, the first step would be protonating the hemiacetal with HCl. And so the hemiacetal, you might recall, has an OH and it has an oxygen and an R group attached to that oxygen. So you can think of this as a alkoxide and an alcohol attached to the same carbon. Once you protonate the hemiacetal or hemiketal, you get this intermediate, which basically has the oxygen of the alcohol protonated as a water molecule. It's a good leaving group, and so we can push it out by using the lone pairs on the alkoxide. Remember, the alkoxide is what we get when the alcohol adds to the carbonyl. That lone pair will push out the water molecule to give you this intermediate. So now the carbon of the what used to be the carbonyl is double bonded now to the oxygen of this ether. That makes this carbon very electrophilic. It's almost identical to a protonated carbonyl. Water, or sorry, not water, but a second molecule of an alcohol will add to this carbonyl, break the double bond, get rid of the positive charge on the oxygen. And now we have this tetrahedral intermediate. We have an OR group, and we have now a second OR group added to the same carbon. That second OR group is from this alcohol that just added. And it is still protonated because we haven't gotten rid of the hydrogen. We could do that in this step. So we could use water, we could use chlorine from HCl to pick up this proton and remove the positive charge on the oxygen, giving us the acetal or the ketal product. A little bit about the hemiacetal to ketone equilibrium. So in general, hemiacetals or hemiketals are unstable, and the equilibrium will be favored towards the carbonyl, whether it's a ketone or an aldehyde. So here's a look at what I'm referring to. If we start off with acetone and we add theoretically one equivalent of methanol, we should get a hemiketal, but that equilibrium is heavily favored towards the carbonyl. The reason for that is carbonyls, the double bond here is a strong bond, and so it favors the equilibrium backwards. Now, the exception to that rule is cyclic hemiacetals or cyclic ketals. So in other words, if we can obtain a fairly stable cyclic hemiacetal or hemiketal, generally that would be the favorite product or the favorite molecule. So here's a look at an example. If we have an aldehyde and an alcohol, that are attached to each other. If we add, or actually if we just let them be, the alcohol will add to this carbon, and the double bond here will be turned into an OH when this oxygen is protonated. So we'll pick up a proton from this alcohol. You'll end up with a cyclic hemiacetal. In this example, the product, the cyclic hemiacetal, is favored over the original aldehyde. One of the best known examples of cyclic hemiacetals is glucose, but this is also true for many simple sugars that can form stable 5 and 6 member rings. So using glucose as an example, we can draw glucose in an open form or in a cyclic form. So this is one way to draw it. This is a straight chain glucose. Glucose has an aldehyde. It has several alcohols. Pretty much every carbon in the six carbon chain has an alcohol. And the one on carbon 5 likes to attack the aldehyde. So here is how that would happen. So here is carbon 5 with this alcohol. That oxygen will attack this carbonyl and form a cyclic hemiacetal. Now, because this is going to lead to a 6-member ring, there's 2 possible conformations that we can draw. We can have this OH that is a result of the carbonyl becoming protonated after attack of the oxygen on carbon 5. This OH can be equatorial, as shown here, or it could be axial, as shown here. As we know from Organic Chemistry 1, equatorial is usually favored, and so it's no surprise that at equilibrium, 69% of all molecules will be found, 63% of all molecules will be found in this form, this conformation, where the OH is equatorial. Only 37% will exist with the OH being axial, and then less than 1% will exist in this open form. Glucose forms 2 well-known polymers called cellulose and starch. Starch is a polymer that forms by glucose molecules making this sugar bond. So on the sugar on the left, we see an axial bond, and that's attached to an axial position of the next sugar unit. And this repeats multiple times to make the polymer, which we call starch. Polymers in general, if you're unfamiliar with that term, just means a very large molecule that has multiple repeating units of the same monomer. In this case, for starch, it would be glucose. Second polymer that glucose makes is cellulose. It is formed by taking multiple sugar units and making a sugar bond that is equatorial on both sugar units that are connected. Note that humans are not able to metabolize cellulose since they don't have an enzyme that can digest or break down this bond here, which is equatorial. We do, however, have an enzyme that is able to digest the axial bond of starch. One last point that I want to make here is that notice the connection between the 2 sugar units next to each other is essentially an acetal bond. So if we focus in on this carbon here, we have an oxygen and an alkyl group, and then on the other end, we have an oxygen and an alkyl group. So there are 2 alkoxide groups going to the same carbon. That is what an acetal is. The same thing occurs with cellulose. So this carbon here will have 2 alkoxide groups attached to it. So that is also an acetal. Acetals can be used as a protecting group for ketones and aldehydes. Acetals essentially behave like an ether, and so they're very stable. They're stable to bases, nucleophiles, reducing agents, oxidizing agents. The only thing that they're really susceptible to is acidic aqueous conditions, as we'll see in a moment. Now, for protecting aldehydes and ketones, we generally will use a diol, although we don't have to. Diols make it easier to form a cyclic acetal or ketal. That usually is easier to do than just making an acetal out of two equivalents of an alcohol. Here's an example using this ester that also contains a ketone. If we add a diol and an acid catalyst, we can make an acetal from the ketone. Notice that we don't do anything to the ester in this reaction. Now, in predicting the product, we want to look at the diol we're using. This one has 2 carbons. So the acetal will also have 2 carbons, and they're attached to each other, making a 5-member ring to the carbonyl carbon that used to be there. A byproduct of this reaction will be water. And so this reaction, just like any acetal formation, is reversible. If we wanted to remove the acetal protecting group, we can do it with the aqueous acid. Now in this example, I want to illustrate the power of acetals as a protecting group. For example, if we wanted to do a reduction on the ester, that ketone would get in the way because ketones are more reactive towards nucleophiles like hydrides than esters are. So we have to protect the ketone first, and then we could do the hydride reduction of the ester to get a primary alcohol. And then once we're done with that reaction, we could remove this protecting group by using aqueous acid, essentially reversing the formation of the acetal. That will lead us to the ketone plus the diol byproduct. In this question, we're going to try to predict the ketal that is formed from an acid-catalyzed reaction on 2-pentanone with a diol called 1,3-propane diol. So try to do this first before looking at the next slide. 2-pentanone will react with 1,3-propane diol in an acid catalyst to make the corresponding acetal. So the way we want to predict the product is if we take this oxygen and bind it to this carbon, and then we have 1, 2, 3 carbons. So in the product, we have 1, 2, 3 carbons, and then the next oxygen will be attached to that carbon and also attached to the carbonyl carbon. And so the result is a 6-member ring involving 2 oxygens attached to the same carbon. The byproduct will be water. When it comes to amines generally will produce 2 potential products from a ketone or an aldehyde, either an imine or an enamine. The product will depend on what type of amine we use. If we use a primary amine or ammonia, typically we end up with an imine, which you can recognize as having a carbon to nitrogen double bond. Sometimes these imines are called Schiff bases. Another possibility is if we use a secondary amine. Secondary amines will produce instead an enamine. An enamine will have a carbon to carbon double bond and a nitrogen to carbon single bond on the same carbon. If you look closely, enamines are very similar to enols. Let's take a closer look at the reaction between ammonia or primary amines with ketones and aldehydes to produce imines. Here's an example with an aldehyde. If we use a primary amine, you can recognize primary amines by the fact that they have 2 hydrogens in 1 alkyl group. Use a catalytic amount of acid like HCl will produce an imine. So in order to draw the product, you want to take the nitrogen from the amine, place it where the oxygen of the carbonyl used to be, put a double bond there, and whatever alkyl group is on the nitrogen to begin with will also be in the product. The byproduct of this reaction will always be water. This reaction is reversible, so as you'll see in a moment, we can go back from or go from an amine back to the aldehyde by adding water and an acid. Here's another example with a ketone, catalytic amount of HCl, and if we use ammonia, we will get an imine. So notice again, there's a nitrogen to carbon double bond where the carbonyl used to be. In the case of ammonia, instead of having an alkyl group, we have a hydrogen, so you'll have a hydrogen there. We could also use a primary amine here. The result of that would be a similar function group, except there will be an R group where the hydrogen is. This reaction will also produce water, and it is reversible. The reaction works best around a pH of roughly 5, so slightly acidic conditions. Here's the mechanism for the addition of a primary amine or ammonia to a ketone or aldehyde. If we have a primary amine, it will add to the carbon of the carbonyl. So amines are better nucleophiles than water and alcohols, so they can add directly to the carbonyl carbon without the need of an acid first. That gives us an intermediate, a tetrahedral intermediate. And so the next step will be a proton transfer. This oxygen has a negative charge, so it wants a proton. And this nitrogen has a positive charge, so it wants to lose a proton. So this proton from the nitrogen will be transferred over to this oxygen. And usually this is shown in 2 steps, where a base removes the hydrogen and then it will give it to this oxygen. In the next step, which is starts off with a carbonyl amine, the oxygen will be protonated by acid to give us a water molecule. And then this nitrogen can push it out through the lone pairs. And so in the next step, you'll see that there will be a double bond here between carbon and the nitrogen. It continues with an iminium ion being formed. So after the nitrogen has pushed out the water molecule, we'll have a double bond here between nitrogen and carbon. We'll also have a proton on this nitrogen that we're going to remove by using water or some other base in the reaction. And then that would also get rid of the positive charge on the nitrogen. That gives us the final product, which is an imine. As I mentioned previously, the formation of an imine is a reversible reaction. So if we add water, which is the byproduct of imine formation, and we also add HCl, we can reverse that reaction. So here's an example with an imine. If we add catalytic amount of HCl and water, we can turn that imine into a ketone. And you can tell it's going to be a ketone by the fact that this imine is at a carbon that has 2 alkyl groups. So that same carbon will now turn into a carbonyl. The byproduct would be an amine. The amine, you can tell which one is going to be by the fact that we have a nitrogen, a hydrogen, and a methyl group attached to that nitrogen. So adding an extra hydrogen will give us the byproduct from this reaction. Unlike primary amines, which typically give you imines as products, secondary amines will give you an enamine. As you'll see in a moment, the mechanism will explain why that is. Here we have a ketone, an unsymmetrical ketone. If we add a catalytic amount of HCl and a secondary amine, we'll form the corresponding enamine. Notice that in the reaction of an unsymmetrical ketone, the enamine will always form towards the more substituted side. So you can see that the double bond is towards this methyl group, as opposed to the right side of this uh, cyclohexane. On the same carbon of the double bond, we'll have a bond to a nitrogen, which will have two methyl groups, since that is related to this secondary amine that we use here, which has also two methyl groups. The byproduct of this reaction will be water, and this reaction is also reversible, although it's not shown here. This reaction, if we add water and HCl to an enamine, we can make it go back towards the ketone. Here's an example with an aldehyde. If we use HCl in a secondary amine, we can get the corresponding enamines. Aldehydes only have one alkyl group, so there's only one possible place where we can put the double bond. So the double bond will be here, where to attach between two carbons. It is starting where the carbonyl used to be. On this carbon, we'll also have a nitrogen and two alkyl groups. If the secondary amine has two ethyl groups, we'll have two ethyl groups on the nitrogen of the enamine. Byproduct will be water. This reaction, again, is reversible. We can make it go back to the aldehyde by adding water to the reaction. The mechanism for the formation of an enamine, for the first half of the mechanism, it will be identical to the mechanism as forming or when forming an imine. Let's take a look at how this happens. Starting with an aldehyde or ketone, if we add a secondary amine, the secondary amine will add to the carbonyl carbon. Eventually, after a proton transfer, we'll have this carbonyl amine intermediate. So you'll have an alcohol and an amine on the same carbon, making it a carbonyl amine intermediate. In the next step, the oxygen will be protonated, forming water. And in the next step after that, the nitrogen will push out that water to give us an iminium ion, which you'll see on the next slide. Once we get to the iminium ion, this is where things differ between using a secondary amine and a primary amine. In the case of a primary amine, when we get to this iminium ion, we have a hydrogen where this R group is. So the next step was always to remove that hydrogen and basically get rid of the positive charge on the nitrogen. And that led to an imine being formed when we use a primary amine. In the case shown here, we're dealing with a secondary amine that added, forming this iminium ion. And secondary amines by nature have two alkyl groups, as shown here. So when we add base to this step of the mechanism, we cannot remove a hydrogen. And so the only thing that we can do to get rid of this positive charge is remove a hydrogen from an alpha carbon. In other words, a carbon adjacent to the iminium ion double bond. So a base, such as water, will remove this hydrogen, form a double bond there, get rid of this double bond, and put those electrons on the nitrogen to get rid of the positive charge. So that leads us to the final product, an enamine. Similar to imine formation, in the cases of enamines, we can reverse the reaction by adding water and HCl. So as shown here with this example, this enamine will be turned to the corresponding carbonyl and a secondary amine. You can predict the products based on what we're seeing here. So we have a carbon to nitrogen single bond that will turn into a carbonyl, and the amine that is shown here in the enamine will then be expelled. So the nitrogen has to pick up a proton and will become a secondary amine. Amines come in other variations besides your typical primary or secondary amines. So there are certain amine-like molecules like hydrazine, which contain an NH2 bonded to another NH2. And these types of molecules will form what we refer to as imine derivatives when they're mixed with a ketone or an aldehyde. So for example, hydrazine, when mixed with this ketone, NaCl, will form a imine derivative called a hydrazone. So hydrozones are imines of hydrazine. And you can see in the product, we basically have an imine bond between a carbon that used to be part of the carbonyl and the nitrogen of hydrazine. Hydrazine has another NH2 attached to that nitrogen, so that's what you see here in the product. We have water as a byproduct, and also this reaction is reversible, so as you'll see in a moment, we can turn a hydrazone into a ketone in hydrazine by adding acid and water. Another example of an imine derivatives or imine derivative is a hydrazone that has a couple of nitro groups on a benzene ring. So this is referred to as a 2,4-dinitrophenylhydrazine or hydrazone once it becomes the product. So here's an example with acetone mixing with this 2,4-dinitrophenylhydrazine to form an imine derivative, which is a hydrazone. A byproduct of this reaction will be water, and again, this reaction can be reversed by adding water and ACl. A couple of more examples of imine derivatives. So cyclohexanone, when mixed with hydroxylamine, which is NH2 bonded to an OH, will form an oxime. An oxime is another example of a imine derivative. So in the case of hydroxylamine, note that the nitrogen is more nucleophilic than the oxygen. So the nitrogen will attack the carbonyl carbon and form eventually a double bond there. And the OH essentially acts as a substituent that rides along for the reaction and is found in the product. This oxygen from the carbonyl will eventually become a water molecule and it will be a byproduct of the reaction. The reaction again is reversible by adding water and HCl. Here's another example with hydroxylamine again and a different ketone. If we add HCl, we can form the corresponding oxime and water as a product. Note that many imine derivatives are highly crystalline, and so sometimes, especially if you don't own an NMR, which is a pretty expensive instrument, certain labs will turn ketones and aldehydes into imine derivatives, and they'll take the melting points and figure out the other physical properties and use those to determine or confirm the structure of an unknown. Aldehydes or ketones can be determined or confirmed, their structures confirmed by turning them into a 2,4-dinitrohydrazone, as shown here in this reaction. This product is highly crystalline. It also forms a very red color. Those characteristics plus the melting point will allow a particular ketone to be compared with a set of standards, and you can use that to determine or confirm the structure of a particular unknown aldehyde or ketone. Of course, if you have NMR and IR and mass spec available, those methods would make it a lot easier to identify the unknown. But in certain labs, those are not available due to cost, and so this is a simple method to determine or confirm the structure of an unknown aldehyde or ketone. For oximes and hydrozones and other imine derivatives can be hydrolyzed and converted into the corresponding aldehyde or ketone. Here's a couple examples, starting with an oxide. If we add water and HCl, we can convert it to the corresponding ketone plus hydroxylamine. You can tell you're going to get hydroxylamine by the fact that the nitrogen has an OH in the imine derivative. And then the ketone will simply come from the converting this imine bond to a carbonyl, which you see here in the product. With the next example, we start off with a hydrazone. And so this hydrazone will be converted into a carbonyl, and we'll get a hydrazine byproduct. Beta-carotene is a natural compound that has multiple double bonds that are conjugated to each other. This conjugation gives beta-carotene an orange color, and many fruits and vegetables like carrots and mangoes and cantaloupes have this orange color due to beta-carotene. Beta-carotene is a compound that is converted in our bodies into cis-retinal by an oxidation reaction that turns or gives the product an aldehyde. This aldehyde will react with the amino group of a protein called opsin to form an imine bond, similar to the reactions we learned in this chapter. And rhodopsin, which is the product from this reaction, is a light-sensitive protein found in the retina of our eyes, and is essential for low light vision. Nucleic acid bases cytosine and uracil can be interconverted through a tautomerization followed by a deamination reaction. Starting with cytosine, we can convert this amino group into an imine through a tautomerization reaction. Notice the double bond shifts from being in between this carbon and nitrogen to being in the other carbon and nitrogen in the amino tautomer. Hydrolysis of this imine by adding water will lead to a carbonyl being formed, which is the structure of uracil. Cytosine is found both in DNA and RNA, while uracil is found in only RNA. In this question, we'll practice the acid-catalyzed addition of amines to cyclohexanone. In the first question, we're using a primary amine. In the second question, we'll use a secondary amine. Ketones and aldehydes can be reduced completely and turned into an alkane by a reaction called the Wolff-Kishner reaction. As an example, starting with a ketone, if we add hydrazine, we'll initially get a imine derivative, a hydrazone, which will then react with base while heating to be eliminated into an alkane. The reaction produces N2 gas and water as a byproduct. Note that evaporation of this nitrogen gas essentially turns the reaction into an irreversible reaction since it will be difficult to capture the nitrogen gas after it has evaporated. In the second example, we're using acetophenone reacting with hydrazine, again under basic conditions while heating will remove completely the carbonyl and produce nitrogen gas and water as byproducts. Let's take a look now at the mechanism for the Wolff-Kishner reaction. The reaction starts by hydrazine attacking the carbonyl of the ketone or aldehyde, and then through a series of steps, we will eventually produce the imine derivative, which we see here. Note that this is the same mechanism we saw in the last section. Addition of base to the imine derivative will result in removing this hydrogen, putting a negative charge on the nitrogen, as shown here. And then that nitrogen will push electron towards the carbon to put a negative charge on the carbon. Note that these are resonance structures of each other. Water will then protonate that carbon to produce the intermediate that we see here. If we repeat the same two steps again by adding base, removing this hydrogen, and eventually putting a negative charge on this carbon, we can continue the reaction. In the last couple of steps of the mechanism, the nitrogen will be removed as N2 gas, and it results in a negative charge on the carbon. Addition of water will protonate the negative charge on the carbon, as shown here. So this carbon will pick up a proton from the water to add an extra hydrogen there, and overall we have turned the ketone into. Here's another example of a ketone being reduced with hydrazine and under basic conditions. So this ketone is completely removed into the corresponding alkane. Note that we have the same number of carbons, so there are 3 attached to the ring. We'll have 3 in the product as well. We can do the same reaction with aldehydes, so this aldehyde will be reduced under the Wolff-Kishner reaction into the corresponding alkane. Let's now practice some examples of the Wolff-Kishner reaction. So the question here asks us to show how you would prepare the following compound, which is shown here, from the following ketone, which is 4-methylpent-3-ene 2-one. And in the next reaction, we're going to take 4-methylpentane 2-one and attempt to convert it into this alkane. So the reaction is essentially asking us to give the reagents for the reaction. In order to turn this ketone here into the corresponding alkane, we will use the Wolff-Kishner reaction. So that involves hydrazine, potassium hydroxide, and although it's not shown here, we generally will heat this reaction well over 100 degrees. We can do the same reaction with the ketone on the bottom under the same reaction conditions. A complementary reaction to the Wolff-Kishner reaction is the Clemmensen reduction. So this reaction does the same thing as the Wolff-Kishner. It turns ketones and aldehydes into alkanes. However, it does it under acidic conditions. So here's an example of the Clemmensen reduction. Starting with a ketone, if we add HCl, zinc, and mercury, we can convert it into an alkane. We can remove an aldehyde carbonyl in a similar fashion under HCl, zinc, and mercury. Notice that we retain the same number of carbons in the product. Reaction in organic chemistry is called the Wittig reaction. This reaction starts off with triphenylphosphine. We add that to an alkylating agent such as methyl bromide. Through an SN2 reaction, this phosphorus will attack the carbon, eliminate the leaving group, and form a phosphonium salt. Phosphonium salts will have a positive charge on the phosphorus, which makes the hydrogens on this carbon fairly acidic. We can add a strong base like butyllithium to remove one of these hydrogens and therefore produce what we call a Wittig reagent or a phosphonium ylide. The phosphonium ylide will have a negative charge on the carbon, which makes that carbon very nucleophilic, and it also will have a positive charge on this phosphorus. Ylides are compounds that contain both a positive and a negative charge on adjacent atoms. So a good example of that is a phosphonium ylide. Phosphonium means there's a positive charge on phosphorus, and ylide means there is an adjacent negative charge, in this case on a CH2 group. Phosphonium ylides contain two resonance forms, so sometimes they're drawn like this with a positive and a negative charge, or we could use the lone pair from the carbon to form a double bond between the carbon and phosphorus, and you can have a resonance structure as shown on the right here. Either way, we have a nucleophilic carbon next to the phosphorus, which allows the Wittig reaction to occur. The Wittig reaction is used to convert a carbonyl, like a ketone or aldehyde, into an alkene. Here's an example with cyclopentanone. Using this Wittig reagent, we transfer the CH2 and the double bond into the product. So as you can see, this carbon that is part of the double bond on the end, it has two hydrogens, just like the Wittig reagent. So you can essentially visualize this reaction as swapping an oxygen for a CH2 group. Some Wittig reagents, as you'll see in a moment, will contain alkyl groups rather than hydrogens, and those will be transferred as well. The byproduct of the Wittig reaction is always triphenylphosphine oxide, which is a sometimes difficult to remove byproduct. Sometimes when we do chromatography to purify our desired product, sometimes it is very difficult to remove this compound. The mechanism for the Wittig reaction occurs as follows. So the Wittig reagent involves a carbon that is nucleophilic. That carbon will attack the carbon of the carbonyl. It will produce this intermediate, which will lead to the oxygen and its negative charge attacking the phosphorus with its positive charge, forming this four-member ring. That four-member ring is very strained, and it will decompose to either go back to the original ketone or ylide or go forward into producing this alkene and triphenylphosphine oxide. Note that the phosphorus to oxygen double bond is a very strong bond, and so there is a driving force to produce these two products that you see here at the end. If we use an unsymmetrical Wittig reagent and an unsymmetrical aldehyde or ketone, we can produce a product that has a mixture of E and Z isomers. In general, alkyl ylides, so as shown here, typically will give the Z isomer. However, there are conditions we can use to produce the E isomer. We won't go into those details. For our course, just assume that you can get whichever isomer you need. Note that esters and amides don't really react with Wittig reagents, so we can do a Wittig reaction with an aldehyde or ketone in the presence of one of these functional groups. Also, a hydrogenation reaction of the alkene product will allow you to overall convert a carbonyl into an alkyl substituent. Here's an example to illustrate those 2 points. This compound has a ketone on the left and an amide on the right. If we do a Wittig reaction with this Wittig reagent, we will add the Wittig reagent, or at least the alkyl group on it, to where the carbonyl of the ketone was. Notice there are 1, 2, and 3 carbons. So 1, 2, and 3 carbons will be added where the carbonyl, the ketone, was. Nothing happens to the amide. Now notice in this product, there is no double bond. That is because we're doing a hydrogenation reaction following the Wittig reaction. Normally, we would obtain a double bond here where the carbonyl used to be, but if we do a hydrogenation, we'll get an alkane there instead. The Wittig reaction is a reaction that has been used for a number of syntheses of important biological molecules. For example, it has been used to synthesize vitamin A. In this synthesis, an aldehyde, as shown on the right, was used. Notice it had also an ester in the molecule, and mixing that with a phosphonium salt will lead to producing a Wittig reagent by addition of base. So sodium methoxide will deprotonate one of the hydrogens on the CH2 group, turning that into a Wittig reagent. Under reversible conditions, meaning under or with a protic solvent, we can allow the E isomer to be favored. This Wittig reagent will react with the aldehyde to produce the double bond highlighted here in color. Again, because of the reversible conditions, we obtain the E isomer. If we didn't have these reversible conditions, we would obtain the E isomer instead. This question, we will use the Wittig reaction to produce the following two alkenes. So the question asks what carbonyl compound and what phosphorus illite would be used to prepare the following compounds. In order to think about the Wittig reaction backwards, we want to think about splitting the double bond of the product, the alkene, into two parts, turning one side into a ketone and the other side into an illite. So as you can see here, we obtain, or we would do this reaction from cyclohexanone and the following illite. So the illite always has triphenylphosphine attached to the alkyl group that we're going to add to the carbonyl. Now you might recall that Wittig reagents are typically made from an SN2 reaction. Typically it involves triphenylphosphine adding, so that would be the following compound, triphenyl, so 3 phenyl groups attached to a phosphorus, and that typically reacts with an alkyl halide through an SN2 reaction. For that reason, we want to make sure that the alkyl halide does not have a lot of sterics. So if we wanted to make the following Wittig reagent, we would use perhaps ethyl bromide as shown here, and that should lead to the following Wittig reagent after we use base. So initially you'll produce a phosphonium salt, and then base will remove the acidic hydrogen. So imagine this having a CH2 group. A base like butyllithium will remove a hydrogen from there to produce this Wittig reagent. We can draw the Wittig reagent as shown here, or we could get rid of those charges and instead add a double bond here. Either way is fine. Now, my main point that I wanted to make here is that because this Wittig reagent is made from an SN2 reaction, we want to make sure that there isn't a lot of sterics around the alkyl halide in order to produce it. So ideally, a primary alkyl halide would work best. So for that reason, in order to make this ketone, we would want to use this particular Wittig reagent and this particular ketone as opposed to breaking the double bond the other way, where this becomes the ketone and this becomes the alkyl halide. That would make the alkyl halide a secondary alkyl halide plus it is part of a cyclohexane ring, which are not helpful for the SN2 reaction. In the next example, again, if we split the double bond, we can make one side a ketone, the other side a alkyl halide. So given that this carbon has two alkyl groups, we want to turn that into a ketone, which would be acetone. And then on the left side, the carbon has a hydrogen and a phenyl ring, so that would be a primary alkyl halide we can use to make the following Wittig reagents. Let's now review a reaction that we've seen previously in the chapter with alcohols. So you might recall that ketones and aldehydes will react with Grignards and organolithiums in order to produce an alcohol. So if we start off with a ketone and we add a phenyl Grignard or phenyl lithium reagent, we would transfer a phenyl group to the carbon of the carbonyl and turn the ketone into a tertiary alcohol. With aldehydes, when we react with Grignards and organolithiums, we'll transfer the alkyl group to the aldehyde carbon. So in this example, the CH3 group shown here will add to this carbon and turn that carbon into a secondary carbon now, and the product will be turned into an alcohol, a secondary alcohol. We can add a cyanide nucleophile to aldehydes and ketones as shown in this reaction. So typically the reaction will involve catalytic amount of potassium cyanide and a large amount of cyanide gas. So this is a pretty dangerous reaction, but it allows us to turn an aldehyde into a cyanohydrin, which is a functional group involved in a carbon that has both a cyano group and a hydroxyl group. Here's the mechanism of the reaction. The cyanide ion will add to the carbonyl carbon, break the double bond to give us this tetrahedral intermediate. The oxygen will then be protonated by cyanide gas to produce the cyanohydrin and the cyanide ion, which will continue the reaction. So for that reason, we only need a catalytic amount of potassium cyanide. Note that cyanide ion is not a strong enough nucleophile to react with esters and amides, so it generally reacts only with aldehydes and ketones. Certain species of millipedes as well as plants release hydrogen cyanide as a deterrent for animals that threaten them. For example, millipedes will use this sugar compound that they obtain from their diet of fruits, for example, from apricots or wild cherries or peaches, and they will, when threatened, convert it into mandelonitrile, which is a compound that is a cyanohydrin. This cyanohydrin can expel hydrogen cyanide, and therefore it can be used to deter animals from eating or bothering the millipedes. The reactions we just covered, we want to attack this question, which will ask us to show the structure of the cyanohydrin obtained from cyclohexanone. If we use cyclohexanone to make a cyanohydrin, the reaction will occur as follows. So the carbonyl carbon will be attacked by cyanide to produce this tetrahedral intermediate, which will then be protonated to produce the following cyanohydrin.